System noise temperature and G by T ratio. First, we need to understand the noise temperature. Noise temperature is a useful concept in communication receivers since it provides a way of determining how much thermal noise is generated by active and passive devices in the receiving system. It is not exactly the actual temperature. This is equivalent noise temperature, mind it. At microwave frequencies, a black body with a physical temperature Tp degrees Kelvin generates electrical noise over a wide bandwidth, right? So noise power can be written as Pn equal to K into Tp into Bn, where K is the Boltzmann constant. This is the value. T suffix P is the physical temperature of the source in Kelvin, degree Kelvin, and Bn is the noise bandwidth. So Pn is the available noise power and will be delivered only to a load that is impedance matched to the noise source. Now this term K into T suffix P is a noise power spectral density in watt per hertz. The density is constant for all radio frequencies up to 300 gigahertz because 300 gigahertz is said to be the range of upper limit of the RF radio frequency. We need a way to describe the noise produced by the components of low noise receiver. So this can conveniently be done by equating the component to a blackbody radiator with an equivalent noise temperature written as Tn Kelvin, not degree Kelvin, Tn Kelvin. A device with a noise temperature of Tn Kelvin produces at its output the same noise power as a black body at a temperature Tn degree Kelvins, followed by a noiseless amplifier with the same gain as the actual device. So this is how we define the noise temperature or equivalent noise temperature. Noise temperatures from 30 Kelvin to 200 Kelvin can be achieved without physical cooling if gallium arsenide FET amplifiers are employed. Gallium arsenide FET amplifiers can be built to operate at room temperature with noise temperature of 30 Kelvin at say 4 GHz and 100 Kelvin at 11 GHz. Typically, noise temperatures increases with frequency and an LNA, low noise amplifier, for a 20 GHz receiver might have a noise temperature of around 150 Kelvin. Okay. See, noise temperature higher means it is generating high amount of noise. Simple as that. Okay. So our objective should be to keep the noise temperature as low as possible. Okay. And noise temperature is actually related to the noise figure of the system. How an amplifier can have a noise temperature that is lower than physical temperature? See, physical temperature of a antenna receiver is the room temperature, right? Or very close to room temperature. But noise temperature, as per noise temperature is concerned, it is maybe of the order of 100 Kelvin or 30 Kelvin, right? But 30 Kelvin means it is extremely cool temperature. So obviously it is not a physical temperature, right? So how the noise temperature becomes so low compared to the physical temperature? So let us try to understand it. Noise temperature simply relates the noise produced by an amplifier to the thermal noise from a matched load at the same physical temperature placed at the input to the amplifier. If the amplifier produced no noise at all, its noise temperature would be 0 Kelvin. If the amplifier produces less noise than a matched load at the same physical temperature, its noise temperature will be lower than its physical temperature. Got it? So that is why the noise temperature becomes much lower compared to the physical temperature, because it is not exactly that actual temperature. You cannot measure this noise temperature with the help of thermometer. It is not like that. It is a way of representing the noise power. Get it? It is way of representing the noise power. We are representing noise power in terms of temperature, right? If the overall end-to-end gain of the receiver is GRX and its narrowest bandwidth is BN hertz, the noise power at the demodulator output should be PNO equal to K into TS BN into GRX watt. Well, this GRX is the gain at the receiver from RF input to the demodulator input. The noise power referred to the input of the receiver is PN, where Pn can be written in this way: KTS into Bn watt. Let the antenna deliver a signal power of PR watts to the receiver RF input. The signal power at the demodulator input is PR into GRX, right? Representing the power contained in the carrier and sidebands after amplification and frequency conversion within the receiver. So the carrier to noise ratio at the demodulator can be written in this way: C by N, that is equal to PR into GRX divided by, this is the carrier part, divided by the noise part, KTS BN into GRX, right? So GRX, they are the same. So PR divided by KTS into BN, right? The gain of the receiver cancels out in the equation, so we can calculate C by N ratios for our receiving terminals at the antenna output port. This is convenient because a link budget will find PR at this particular point, right? Using a single parameter to encompass all of these sources of noise in a receiving terminal is very useful, because it replaces several sources of noise in the receiver by a single system noise temperature TS. So we are actually simplifying all the equations, particularly noise as per noise is concerned.